Welcome to this ENME 351 lecture on sampling and aliasing. In terms of the course outline, we've discussed digital logic. We're now moving on from microcontrollers, and we're beginning to look at signals and sensors. In the last lecture, we discussed analog to digital converters, in which an analog signal is input to the ADC, and that analog signal is converted to a digital code or digital representation. And so a next logical question should be, well, how fast can I convert that analog signal to a digital representation before I am no longer able to accurately represent the frequency content within that input analog signal? With that in mind, let's take a look at our quick one-slide review from our video lectures. If we have an analog signal input to our ADC, and we're sampling that input signal at some frequency fs, we can then define a Nyquist frequency. And the Nyquist frequency Fn is equal to Fs over 2, so it's 1/2 of the sampling frequency. Thus, the Nyquist frequency defines the maximum frequency content I can expect to recover from the sampled signal. So I have an input analog signal input to my ADC at some input frequency, and I'm sampling that signal with my ADC at Fs. As a result, I have a Nyquist frequency Fs over 2. Now, if the input analog signal has a maximum frequency content, we'll call that Fm. If Fm is greater than the Nyquist frequency, then we can expect aliasing to be present in our sampled signal. This then gives rise to the Nyquist-Shannon sampling theorem. The Nyquist-Shannon sampling theorem says I need to sample at greater than 2 times the maximum frequency content of that input analog signal to avoid the presence of aliasing in my sampled signal. In the case where aliasing is present, we can describe the frequency content of that alias signal using a folding diagram. And as you recall from the video lectures, a folding diagram begins then with this baseband here, right? And it goes from 0 up to Fn in really whatever increments we desire. Here I've shown it in 0.25 increments, but it could be 0.25, thirds, tenths, whatever is required to describe the alias signal. So in the case where the maximum frequency content of my input analog signal is less than Fn, we expect no presence of aliasing. However, once we get above 1 times Fn, we start marching our way up the folding diagram, we'll need to fall back to the baseband in order to describe the frequency content of that alias signal. With that in mind then, let's jump into an in-class exercise. So here we have an input analog signal described as y of t is equal to 5 times sine of 18 pi t, and the units are in volts here. The question we pose is this. If we sample this input analog signal with our analog to digital converter, if we sample that signal at Fs equals 12 Hertz, the question is, does aliasing manifest itself in the sampled signal? And if so, what is the alias frequency? At this point, I'd say go ahead, pause the video, work through the solution to the in-class exercise on your own, and then in a couple seconds, we'll work through the solution together. Okay, let's take a look at the solution to this in-class exercise together. So we have an input analog signal described as 5 times sine of 18 pi t. So the first question we should ask ourselves is, well, what is the frequency of that input analog signal? And that's described by 18 pi t, right? So 18 pi will be equal to 2 pi f. As a result, the analog input signal has a frequency of 9 Hertz. We're sampling this input analog signal with our ADC at a sampling frequency of 12 Hertz. So as a result, our Nyquist frequency is going to be 12 over 2 or 6 Hertz. What this tells me then is if I sample this input signal, or any signal for that matter, I can expect to recover frequency content up to 6 Hertz, but nothing greater than that. So anytime I have an input signal, an input analog signal to my ADC greater than 6 Hertz, I expect to see aliasing. So as a result, aliasing will show up in this sampled signal. If we continue then, we have 9 Hertz. That'll be equal to 1.5 times Fn, where Fn is 6 Hertz. So we'll need our folding diagram to solve this problem. Let's start on the baseband of our folding diagram, and let's work our way up to 1.5 Fn. Here's 1.25, here's 1.5, and we'll need to fall back down then to 0.5 FN. So as a result, our alias frequency, that'll be equal to 0.5 FN, 0.5 times 6, or 3 Hertz. If we take a look at these signals with respect to time, here's our input signal. Signal in blue is 5 times sine of 18 pi t. We're sampling that signal at 12 Hertz. And if we reconstruct this sampled signal using linear interpolation, here then is what the analog to digital converter believes is the original input analog signal. This is the reconstruction of the sampled signal. And of course, this 3 Hertz signal is slower in terms of frequency than the input 9 Hertz, right? So we have an alias or a false frequency being reconstructed by our sampled signal. Let's continue the in-class exercise, and now we have increased the frequency of that analog input signal. Here we have a signal varying as y of t is equal to 5 times sine of 30 pi t. We're going to sample it at the same sampling frequency, 12 Hertz, and the same questions are posed, right? Does aliasing exist in the sampled signal? And if so, what is that alias frequency? Once again, I'd recommend go ahead, pause the video, and in a couple seconds, we'll walk through the solution together. Okay, let's take a look at the solution to this in-class exercise. Well, we have a sine wave oscillating at 2 pi f is equal to 30 times pi. Therefore, the frequency of that input analog signal is equal to 15 Hertz. We're sampling at 12 Hertz again, so that Nyquist frequency, that'll be 6 Hertz, right? That, once again, is the maximum frequency content I could expect to reconstruct in my sampled signal. Well, 15 Hertz is greater than 6, so we're definitely going to have aliasing present in our sampled signal. To evaluate that aliasing, we know that 15 Hertz, that's equal to 2.5 times 6. So we'll need to go back to our folding diagram and work our way up to 2.5 times Fn. Once we're at 2.5 times Fn, we'll fall back down to this baseband here, and we'll fall back down to 0.5 times Fn. So as a result then, the alias frequency present in our sampled signal, that'll be 0.5 times Fn, 0.5 times 6 will be 3 Hertz. Right, so even though we've increased the frequency of the input analog signal, we're going to see the same alias signal in our sampled data. If we look here at that input analog signal, this is a 15 Hertz sine wave, and let's sample it at 12 Hertz again. Reconstructing that signal with a linear interpolation, we'll find that the analog to digital converter thinks this was actually the input analog signal, which is of course slower than the 15 Hertz input, right? So in both cases, we have a input analog signal of 9 Hertz, then of 15 Hertz, but in both cases we're sampling at 12 Hertz. As a result, the sampled signal will alias down to 3 Hertz in both cases. There are a host of examples of aliasing in everyday life. For example, if you've driven down a highway at night and looked at the wheels of the car next to you, let's say you have 2 cars in 2 parallel lanes and you drive up next to a car, you may have noticed that at certain speeds, it actually looks as if the wheels of the car are going backwards, right? And you may say to yourself, what is going on there? Well, that's aliasing. That's aliasing due to the frequency with which the lights that line the road are oscillating relative to the angular velocity of the spokes of the wheel. And so this is a common phenomenon known as the wagon wheel effect, as we can see here. Of course, with the wagon wheel effect you see in the video, it's not the lights that are oscillating as you drive down the road, it's the frame rate of the camera. Here's another example of aliasing in the real world. Similar effect, right? We have a camera operating at some frame rate, right? It's taking frames of the video at some frequency, and it's stitching those together to make a video. It just so happens to be in this example that the frame rate of the camera is aliasing down the frequency input to the camera, the frequency of the bird's wings oscillating, and it looks as if the bird is just hovering there. Let's jump into another in-class exercise then. Here we have an input analog signal, which has now two frequency components. So y of t is equal to 1000 times sine of 40 pi t plus 500 times sine of 150 pi t. And the units here are in lux. The same questions are posed. Does aliasing present itself in the sampled signal if I sample this input analog signal with an ADC operating at 100 Hertz? Once again, I'd recommend go ahead, pause the video, work through the solution on your own, and in a couple seconds, we'll work through the solution together. Okay, let's take a look. Here we have an input analog signal, which now has two frequency components, right? 40 pi and 150 pi. So we need to describe those in terms of Hertz. We're going to sample this input analog signal at 100 Hertz. As a result, the Nyquist frequency will say, okay, I can see frequency content in my sampled signal up to 50 Hertz, but nothing greater than that. Well, we have a 40 pi signal, that'll be 20 Hertz. And we have a 150 pi signal, that'll be 75 Hertz. Okay, let's take a look then. We know that Nyquist says we can see frequency content in our sampled signal up to 50 Hertz. Well, as a result, we'll be just fine with the 20 Hertz signal. There'll be no aliasing manifesting itself. However, in the 75 Hertz signal, we will have aliasing manifesting itself. So we need to go through the exercise of a folding diagram and explore the aliasing frequency that arises from the 75 Hertz input analog signal. We know that 75 Hertz is equal to 1.5, or I say here 3 over 2 times 50. 50, once again, is that Nyquist frequency. And we need then that folding diagram to describe the alias frequency. So let's move along the folding diagram from 0 Fn up to 1 Fm up to 1.5 Fn. And we'll need to go ahead and fall back down to the baseband here. Okay, so we'll be looking at 0.5 Fn. Thus, the alias frequency component of the 75 Hertz input signal, that'll be 1/2 Fn or 25 Hertz. Here's a description of 25 Hertz in terms of a radial velocity, right? Radians per second. And thus we can describe the sampled signal as a discrete signal because I'm sampling it. Thus you have the brackets. That'll be equal to 1000 times sine of 20 Hertz, or in this case, 40 pi t, times n, right? Instead of t, in terms of time, it would be n, would be discrete samples, plus 500 times sine of 50 pi t. And once again, we're not using t because it's discrete, so it'll be 50 pi n. Let's take a look at these results graphically then. Here is our input signal. We have a input analog signal with two frequency components. 1000 times sine of 40 pi t plus 500 times sine of 150 pi t. So as a result, there was that 20 Hertz signal, sort of that slower signal, and riding on top of that is that faster 75 Hertz signal. We're going to sample this input analog signal at 100 Hertz. And let's go ahead and stitch these samples together using linear interpolation. So as a result then, this is the signal that the analog to digital converter believes is actually input to the ADC. And what's really interesting about this signal, if you compare it to the original analog input signal, is that we've maintained that 20 Hertz slower signal just fine. There's no aliasing present, but we've effectively lost the ability to reconstruct that higher 75 Hertz signal. So as a result, you've lost the ability to reconstruct some of this higher frequency content in the blue while being able to reconstruct the slower 20 Hertz signal just fine, right? So as a result of sampling this signal at 100 Hertz, we have no aliasing existing. We can reconstruct the 20 Hertz signal just fine, but we've lost the ability to accurately reconstruct the 75 Hertz signal component that's now aliased down to a 25 Hertz component. Let's go ahead and wrap up this lecture with a few quick notes on sampling and aliasing. You have to note here, aliasing is not the same as low-pass filtering. It's not the same as low-pass filtering, right? There is no filter in line from this input analog signal to the ADC. It may appear to have a similar effect in terms of the data, but it is not low-pass filtering. It's not the same thing. Now, you can add a low-pass filter, as I just mentioned, in line to minimize some of the problems with aliasing if needed, but that's really up to the engineer to decide if that's required for this particular application. And the big takeaway here is, well, how do we avoid aliasing? And I'd say a good rule of thumb is to use a sampling frequency of about 5 to 10 times the maximum frequency content of the original input analog signal. If you're using them 5 to 10 times, for sure you're going to avoid aliasing, and this will be less and less of a problem. Now the question is, why not increase that? Why not do 50 times the maximum frequency content, 100 times? And at some point you end up having so much data to save that it's not exactly useful, right? You're able to reconstruct that signal just fine without all the extra data. So a good rule of thumb then, 5 to 10 times FM. Last thought here, we had discussed in the last lecture the analog to digital converter on your Arduino Uno, right? That's a successive approximation register ADC. And if you notice here from the Arduino reference page that the ADC on the Arduino Uno can sample at about 10 kilohertz, right? At about 10,000 times per second. So now you can say to yourself, oh, interesting. If I have a limit on the frequency with which I can sample an input signal to the Arduino Uno, I therefore have a limit on the maximum frequency content of an input analog signal that I could accurately reconstruct from the data.